So in this lesson, we're talking about Kirchhoff's laws. Gustav Kirchhoff was a physicist who did some work with circuits and identified two laws that really helped us to understand how voltage and current work in various circuits. So his two laws are written here on this slide, one for voltage, one for current. So the voltage law says that in each closed loop in the circuit, the voltage gains are balanced by the voltage losses. So the net voltage is zero in each loop. So you'll see what I mean, hopefully later when I show you pictures of actual circuits. I'll point out what he means by a closed loop and also point out what he means by voltage gains being balanced by the voltage losses. But this has to happen in every closed loop in a circuit. And then he has another law for current. It says at each junction in a circuit, the total current flowing in equals the total current flowing out. The current only changes at junctions. So current is how fast the charges are moving, basically how fast the charges are moving. And in some parts of the circuit, these blue dots will be moving a bit faster, and in other parts they'll be moving slower. So what he's saying is that whatever the speed is going into a junction point, which is where paths split up or connect together, whatever the current is going into it has to equal the total of the currents flowing out of it. So I'll show you what that means in future slides as well. So there's one law for voltage, one law for current. We're going to try to apply them to various circuits. So I'm going to start with a series circuit. Okay, just a simple series circuit. So this one's got one cell, one light bulb, and one resistor. So in a series circuit, there is only one loop. So what I mean by a loop is taking a path that starts at one terminal of the battery, goes around wires and loads and whatnot, and returns to the other terminal of the battery. Okay, so starting at one end of the battery, going around some stuff, and coming to the other end of the battery, that's called a loop. So in a series circuit like this one, there's only one loop. Okay, there's only one loop. And the voltage law says in each closed loop, the voltage gains are balanced by the voltage losses. So in this circuit here, I labeled the voltage gains and losses. So voltage is gained by charges across the battery. Okay, so there's positive 3 volts that the battery is giving to the charges, something like that. And then this positive 3 volts, Kirchhoff is saying, has to be balanced out by voltage drops at the loads. So there's two loads here. There's a resistor, which uses up some volts or some energy, and there's a light bulb that uses up some volts or some energy. So I've labeled how much voltage is dropped across each load, -1 for the resistor and -2 for the light bulb. And these two drops must add up to the total gain. So that's what the Kirchhoff's voltage rule is saying. Okay, those total voltage drops must add up to the voltage gains in every loop in a circuit. Now what about the current? So the current law says that at each junction in a circuit, the total current flowing in equals the total current flowing out. So that has to do with amps. So I've labeled the amps in the circuit. It happens to be 0.20 amps. And this 0.20 amps is going to stay the same until it reaches some kind of a junction point. But in a series circuit, there's no junction point. Okay, there's no point where the circuit splits off into multiple paths. There's only one path in a series circuit. So therefore, the current never splits off at all. It's 0.2 amps all the way through. So this is the circuit I built right here. I could plug in an ammeter to measure the current. And what I'm trying to say is no matter where I plug this ammeter in, it should give the same reading of 0.2 amps. The blue dots are moving at a certain speed, and that speed is the same everywhere in the series circuit. And actually that makes sense, because if they were going faster somewhere and slower somewhere else, then they'd be bumping into each other. So in order for them to avoid bumping into each other, they all have to be going at kind of the same speed. So I'll just plug it in right at the battery here, and oops, and it says 0.2 amps. That's how fast they're going. 0.2 coulombs every second pass by that point. I can try somewhere else. I'll try right here. Break that up. Put the ammeter in. And it also says 0.2 amps. There's on average 0.2 blue dots passing through this thing every second. So that's the current law. The current stays the same until it meets some kind of a junction. But you won't have any junction in a series circuit. But in a parallel circuit, you will. So the next example is a parallel circuit here. And I'll start with voltage again. So, first of all, just take a look at this circuit as a whole. It's got two batteries. And then there's actually two loops this time. There are two loops. So a loop starts at one terminal of the batteries, goes around some stuff, and comes back to the other terminal. That's a loop. So my mouse right now is tracing one loop. Battery, going up the middle path, and going back to the battery. Okay, that's one loop. And then the second loop would be from the batteries all the way to the outside where there's a resistor and a light bulb, and then all the way back to the battery. So my mouse is now tracing the second loop in this circuit. Okay, so there's two loops here. And Kirchhoff's voltage rule says that in each of those loops, the voltage gains are balanced by the voltage losses. So we have to look one loop at a time to analyze that. So if I were in the classroom, I'd be covering up half the circuit with my hand and just analyzing the first loop here. Okay, so looking at the first loop, what are the voltage gains? Well, the voltage gains happen at the batteries. So there's a positive 6-volt gain. And then going off the first loop, this is a voltage drop of negative 6 volts. And then that's it. Okay, so positive 6 volts gets balanced out by negative 6 volts. That's Kirchhoff's voltage rule for the first loop. Now let's look at the second loop. So I have positive 6-volt gain. And then I go all the way here where I have negative 2 volts from the resistor and negative 4 volts from the light bulb. Well, negative 2 and negative 4 make up negative 6. And that balances out the positive 6 from the battery. Okay, so there's Kirchhoff's voltage rule applied to each loop. In this parallel circuit. Now current. Current, the diagram looks kind of complicated here. So I'll start at the battery. So at the battery, the reading is 0.5 amps. Okay, I've labeled it at 0.5 amps. That's basically how fast the blue dots are moving across the batteries, and it's going to be the same speed when it turns a corner and going through this wire here. It's still at a speed or a current of 0.5 amps until it reaches this junction point. It reaches this junction point, and Kirchhoff's current rule says that at the junction, the total current flowing in equals the total current flowing out. So if you look at the numbers I have labeled, I have 0.5 amps flowing into this junction. Now flowing out, so this splits off into two paths. One path going up, and the current there is 0.3 amps. And the other pathway from this junction point would be going to the right. And I've labeled the current there as 0.2 amps. So basically what happened was this 0.5 amp current reaches this junction and gets split up. It gets split up into 0.3 and 0.2. Now notice that they're not equal. Okay, they're not equal. Sometimes they're equal, sometimes they're not. It depends on what you have plugged in to the pathways. See, in one path I've got just one light bulb, whereas in the other path I've got a light bulb and a resistor. So there's actually more resistance in the second pathway here. And when there's more resistance, that's why the current in that pathway is smaller than in the middle pathway. So the 0.3 amps goes up and through this light bulb and then up some more until it reaches this next junction. And as well, the 0.2 amps flows to the right here. It continues, 0.2 amps flows up through the resistor and then through this light bulb and through this wire until it reaches this junction as well. So the 0.3 amps and the 0.2 amps combine back together at this other junction. They combine back together to make 0.5 amps again, which goes back to the battery. And then it just kind of loops around in a cycle. So I've got that circuit built here. So you may be able to see that the blue dots are moving relatively quickly through the battery and through these wires, but they're moving slower up the middle path. Okay, they're moving slower up the middle path compared to through the battery. And they're moving even slower up the far path, which has the resistor added to it. More resistance makes it even slower. Okay, so this junction point is kind of where the change of speed happens. It's going fastest coming into the junction, but when it splits up into the two paths, they're slower in those two paths. All right, so there's an example of a parallel circuit, and one more example is a mixed circuit. So it's got some parallel and some series. So I'll start with the voltage law. So first of all, how many loops are there in this circuit? There's 3 loops. So if I start at the battery, I go this way, I can go down the first path and back to the battery. That's 1 loop. Second loop, start at one end of the battery, go straight, go down the middle second pathway, and then return to the battery. That's considered a loop. Third possible loop, start at one end of the battery, go all the way down to the end, go down the right path, and go back to the battery. That's the third possible loop in this circuit. So this circuit's got 3 loops. In each loop, let's count the voltage gains and losses. So the voltage gains are simply 9 volts from the battery. It's a more powerful battery. Voltage drops in the first loop. So it drops by negative 6.75 volts after the first light bulb. And then no matter which path I go down, there's one light bulb. So that light bulb takes up negative 2.25 volts. So it's negative 6.75 and negative 2.25 add up to negative 9. So there's a negative 9 volt drop to match the positive 9 volt gain. Same thing happens no matter what path you go down. I'll go down the middle path. So I got a 9 volt gain at the battery, 9 volts minus 6.75 volts, and then minus 2.25 volts. That brings me back to 0. Voltage gains equals voltage losses. So that's the voltage. I don't have much time to talk about the current. I'll just still show the slide. So I've got 0.66 amps at the battery, 0.66 amps to the first light bulb as well. Look, there's no junction between the battery and the first light bulb here. There's no path splitting. So the current is identical, 0.66 amps, 0.66 amps, till it gets to this junction. It gets to this junction, it splits off. 0.44 goes one way, 0.22 goes the other way. Now I'm going to follow this 0.44 path. This 0.44 amps reaches a second junction. So it splits again into 0.22 one way and 0.22 the other way. So current splits